5 before we say that.
According to his clock, it's 8:30 p.m., which is we're ready to go.
All right. Everybody, welcome to NETVC. Here for the Internet Video Codec Working Group. Sorry, well, testing. Okay. It's really heavy. Welcome to NETVC. So first off, note well, everybody should be familiar with this, but for this particular working group, please make absolutely sure you're familiar with it, because the goal of this working group is to produce a royalty-free video codec. So we definitely need everyone to pay very close attention to the IPR rules in the note well. Start blue sheets around. I think we'll need one, so I'm not going to bother with putting them around. And what always takes the majority of the 10 minutes of chair time, note taker. We need a note taker volunteer. Very terse notes. It doesn't have to be every detail, just major decision points. Any volunteers? Anyone on the Meet Echo want to volunteer for taking notes? Anyone in the Jabber room volunteer for taking notes? We're going to have to impose on someone now. Oh, Nathan did. Thank you very much, Nathan. You took excellent notes last time or the time before. So appreciate that. We have a Jabber scribe volunteer. That's much easier. Just relay in the room. Do you want to do it since we're up here anyway?
Sure.
All right. And we have our guest co-chair. Thank you very much, Matt. All right, so a quick agenda bash. Just going to spend a few minutes, probably not 10, on the status of the current documents. And then Thomas is going to give us an update on the test document. And Steiner will give us an update on Thor and AV1 progress and comparisons, followed by Tim giving an update on DALA 81 transforms. And then Luke is going to give us the latest Chroma prediction from Luma as it's being used in AV1. Any changes people want to make to the agenda? Any other items people want to bring up? If not, let's go on. So quick recap of where we are on our milestones. We have a milestone for the requirements document. That was a work group last called, but because it's being used by some other standards body or some other industry consortia, there may be some substantive changes to it that we foresee coming up pretty soon. So we're holding off on the Shepherd's write-up for now, and we're waiting to see if there's going to be some substantive changes before we progress it onto the ISG. Hopefully that'll conclude within November. So we're going to update the milestone to November and hope to get that done before the end of this month. The testing document, we're going to update that milestone as well because it's not going to be concluded anytime soon. We decided to keep it alive as a living document while the codec candidates are progressing, because we expect the test methodology is going to keep evolving. So we don't want to freeze the document prematurely. So once we have a codec candidate we're comfortable with and a testing methodology we're comfortable with as being pretty stable, then we'll move it on the chain. For the actual codec candidates, we want a single merged codec, and we lack that right now. So we do not have a candidate yet for the milestone for either the codec spec or the reference implementation. So we lack a merged candidate or a merged code base. So you'll see Tim and Steiner presenting different tidbits, but not one consolidated code base or standard. So that's the glaring issue we need to deal with as a work group and try to bring that to closure. Milestone's going to get pushed out to July, so hopefully by then we'll have more clarity on how to come up with a converged candidate. And then finally, there's the milestone for carrying this codec inside of containers, storage formats. So we'll push that out to end of 2018 because that work hasn't even started yet. Any comments on the milestones or the proposed changes to them? All right. So let's go on to first item on our agenda. Thomas, is Thomas on the Meet Echo? Yes, he is. Can you come on over to the queue?
All right, can you all hear me?
Yep. Hear and see.
This is I'm Thomas Stady from Zilla. This is the IETF NETVC testing draft version 6. Next slide. Whoop, that's blank. All right. Is there a slide 2?
Was there something supposed to be on this?
That's just there's it's just two items. So the testing draft has had very few changes between this version and the last version. There was only 2 things. One is small command line changes, and the second one is change to the test scenarios.
Thomas, you're a little faint. Is there any microphone pickup that you can ramp up?
Give me 1 second. Is that better?
Much better, thanks.
Okay. There's a small command line changes and then test scenarios. So next slide. So the first one is the CLI parameters. We've made some small changes to the codecs that we test. One is that we removed a constraint for lag and frames from AOMIC. We previously had forced this to 25, but it turned out that was less than ideal value. It basically buffered way more frames than we technically needed on the encoder. So we decided to drop that out of the command line. As you can see, the command line is pasted on the bottom there. And then we just leave it up to the encoder to pick the maximum reasonable value, which I think is 19 in the current encoder. But the general idea is with the command lines, we want as many, as few possible constraints. We want to impose just the minimum constraints possible and let the encoder pick the rest. So that's in the right direction.
So is that supposed to be crossed through the lag in frames equals 25?
Yes, that gets deleted.
Okay. That should be removed from the command line.
Yep. I pasted the whole command line there, I guess, to show that it was there. But yes, delete that. That's all. Ideally, I'd like to actually drop the auto alt ref setting as well, and that should be automatic, but we haven't changed the code base to do that yet. So that's all. The second slide, or slide number 4. The other problem is that previously we basically only allowed the very slowest encoder modes to be used. For DALA, this was the default, for I think Thor, we had a text file configuration, and for AOMIC, it was CPU used equals 0. And this became increasingly problematic as AOMIC in particular got much, much slower over time. With the current Objective-1 fast suite of videos that's in this testing document, it was taking upwards of 8 days to run the clips. That became impractical for testing, so I basically added an exception that allowed us to run faster test settings under a limited set of circumstances. Basically, if you're only comparing AOMIC to AOMIC, and you are just comparing a code change that just changes a single feature, you're allowed to turn off a couple of the searches, in particular searches for X partition and X partition types. That speeds up it a lot. And as long as you specify I did this, then it's a reasonable usage. This is not certainly ideal. I'm working on a better solution for this. I think a better solution will actually involve custom, speed parameters to the encoder that are better tuned to match a real usage. The one bad thing is that by searching less partition types and sizes, we kind of bias towards smaller partitions and not the rectangular partitions, which is could affect some tools in the negative way. So we're trying to find something better, but this is a stopgap for now. And that is basically the only two changes I've made to the document. I've not had to change the test set or any of the videos at all. Those have stayed pretty much the same.
Okay, so this is Mo virtually from the floor mic. You can be lazy since there's no queue. Just stay up here. The testing methodology itself, though, not the infrastructure, but the testing methodology itself still specifies that the testing should be on the maximum compression, not any other slower mode.
Yeah. So there's basically a section at the end of the testing draft that basically says, different things you can test, right? So you can do like subjective tests, and you can do cross codec comparisons, and there's like objective tests for tools, and that one is the one that we allow to not use the very slowest mode, basically by turning off the X partition search. But if you're doing like a cross codec comparison, you obviously don't want to do that.
I mean, I think I understand why it needs to be done for practical reasons in the infrastructure, but I wouldn't think we want the spec to say this is how we test, right?
Yeah,
ideally, if we didn't have an infrastructure problem, we would test for max compression, right?
Yeah, and that's certainly another issue with doing this is it's a very highly codec specific and implementation specific setting. So it's possible that actually this does not belong in the testing document, and that could be valuable feedback.
Okay. I mean, all codecs will have knobs to adjust the compression speed trade-off. I think it's important for the testing document to state that the objective comparisons will be done at max compression. Otherwise, it's a pretty hard. It's another dimension, another layer of curve, another dimension of curves that we have to look at to evaluate performance. And I know we've presented some of those, and they're useful. Steiner's presented a lot of the speed complexity trade-offs before, but I think it's difficult to put those in the testing document as something that the candidates will be evaluated on.
Right. At the same time, so the one important thing is I don't want to evaluate. If I specify this, I don't want to evaluate the candidates in terms of meeting the requirements criteria on this. This is purely for like individual tools and drafts. In particular, I do want to know, like I think people later will probably present with CPU use settings that aren't 0, and I would like a way to normalize this, so that people use the same CPU use settings and stuff if they need it for speed reasons. But yeah, what we could do is we could just say not specify this in the draft. Maybe say that you may use faster speed settings as long as they're justified, and like external to the draft, basically try to be consistent. That's also a reasonable way to take it.
Okay.
If that's what people would prefer, I can change it.
John Linux. I mean, it seems like with any codec, you could go, your code can go to absurdly slow, right? I mean, and if this is doing, I've heard the phrase frames per day as the speed. I mean, anything could do exhaustive search of every possible bit stream to see which one best matches, in the extreme, your video in the extreme case, and that's just, you can't say we'll use whatever the implementation chooses to make the slowest possible encoding. I think there has to be some threshold of, this is just absurd, we're not going to test this because it has no practical use.
Okay.
I don't know what do other people think. I'll just note that absurd max compression is what's traditionally used in other codec groups, but I'm happy to entertain more practical things in our testing draft.
Any other strong opinions one way or the other? I mean, based on the current feedback, it sounds like I'd like to specify this, but maybe only for the AOM testing and maybe not the explicit exact parameters. And so if anyone, if I'll change it basically so it allows us to do this, but it doesn't specify the parameters. That seems like the middle ground I hear. If anyone objects to that, let me know. Otherwise, I'll do that.
Like you have no objections. Go ahead.
Okay, that's what I'll do for the next draft version. That's all I have to present. So any other comments, or we can be done with this? And
I think we're good. Thank you. All right, next up, Steiner.
Okay, hello everybody. Is this on? Yeah, I have to have it close, I think. I have some updates. Next slide, please. What I have are some updates on the Thor codec, and I also have some updated charts on the performance and compression trade-offs. So this time, the Thor GitHub has actually been updated. It hasn't been updated for a while, so I guess that's about time. The main change is that I've added support for the CDEF filter, a loop filter, which was which has been adopted in AV1. What was adopted in AV1 was the single pass version, which I presented the last time. So this is what I have implemented for Thor. Another change is that I'm working on a faster and simpler audio for CDEF. In Thor is much faster than AV1. So when I first tried to use the audio from AV1, the speed of Thor was roughly halved just for the filter. But I think the audio can be improved, and it's much more easy to experiment with the audio in Thor because Thor is faster and I get the feedback much faster. And whatever I do in Thor could be backported into AV1 as well. And last time I mentioned that I would like to get support for the Dala entropy coder in Thor, but there has been no progress on that. So just see that, but that's the first step towards a merged codec. Next slide, please. Since the last meeting, there have been a few minor changes to CDEF. This is due to a face-to-face meeting we had in the AOM group since the last time. There's a new skip block test. What we had before was that we didn't signal any strength for a filter block if all the coding blocks within that filter block were skipped. But the trouble with that is that you have to decode the entire filter block in order to know whether all the blocks are skipped, and the hardware people don't like that. They want to start the filtering as soon as filtering our coding block as soon as possible, not wait until the end, because they don't like to buffer anything. So it was agreed to change that. So now there's no signaling for the filter block if the coding block size is 64 by 64, meaning that there's no partitioning of that block, and the coding block is skipped. That makes it possible to signal the filter strength just after the skip flag for that block. That adds a slight coding overhead because it means that there will be more signaling and also possibly a slight complexity increase because it also leads to more blocks being filtered. But objectively, the loss is less than 0.1%, and subjectively, I don't think there is a great change. It could even perhaps even be an improvement because we get to do more filtering. Next slide, please. And also recently, AV1 has adopted support for 128 by 128 superblocks. So that also influences how we do the skip test. CDEF still needs to signal at 64 by 64 resolution during the development of CLPF, which was merged with the dollar reading to form CDEF. I tried different block sizes, and 64 by 64 was by far the best size. So we don't want to change that. So for a large superblock 128 by 120, we need to signal up to 4 presets in order to keep the same filter block size. The details haven't been quite decided yet how to do this. We still need to investigate possible compression impacts. But the most simple thing would be just to expand the, instead of testing for 64 by 64 blocks without partitioning, and whether it's skip or not, just to check for 128 by 128 without partitioning. Next slide. So running CDEF instead of CLPF in Thor does give objective gains, just as it did in AV1. I see gains around 1% or 0.5% to 2.2%. I'll show the results on a separate slide shortly. We see quite large gains for Chroma, up to 4%. I'm not quite sure why we didn't see a gain that high in AV1, so I think I'll investigate that. CDEF does add more complexity over CLPF though. It's more processing, but that's not unexpected. I also tried running CLPF on top of CDEF. That gives not much gain, which is not surprising since CDEF is basically a superset of CLPF. But I noted that if I greatly simplify the CDEF RDO, CLPF does give gains, and actually it turns out that CLPF regains almost all of the loss if I simplify the RDO. But having an extra pass of filtering, I think that adds a risk of over-filtering. And also it adds buffer requirements. Is CLPF still attractive for a fast real-time encoder? Currently, it's a good way to speed up Thor, but I think that it's much better. I'd rather to do work on the CDEF RDO. I think it might be hard to make it as fast as the CLPF RDO, but it should be possible to come close without too big losses. Next slide, please. Another change since the last meeting is that in AV1 we have 3 filters applied in cascades: deblocking, CDEF, and then loop restoration, and that adds a lot of buffer requirements. And again, hardware people don't like that. So there was a new proposal from ARM to, and with contributions from Intel, Google, and Mozilla to reduce the buffer requirements. Without that, there's a need of a minimum of 30 lines of line buffers. But with this new proposal, it's possible to reduce that to 16 lines. Next slide, please. So the basic idea is to, there are some normative changes and non-normative changes, and non-normatively, it's possible to do some shifting of the CDEF LR filtering, but the main normative change is that when loop restoration looks outside the superblock that was produced by CDEF, it will read the deblocked output instead of the CDEF output, and that breaks the dependency between CDEF and loop restoration. So the changes that have been proposed requires no normative changes to CDEF. It's mostly in loop restoration, and the changes have no impact on the AV compressed yet results. And it makes the line buffer requirements for AV1 the same as for VP9, 16 lines, even though we have more filters in AV1. And this is moving towards adoption along with loop restoration. It hasn't formally been adopted yet, but it will. Next slide. So a bit more on the encoder complexity on CDEF. As I mentioned, I was working on simplifying the RDO, and I think that can be improved even more. Just as a test how far I could get, I tried to restrict the filter to do no block level signaling. And when I do that, I still get gains, objective gains similar to CLPF. But I think in that case, the subjective gains are still much better than CLPF because we get the directional part of CDEF. So in that case, the encoder will just have to select the optimal strength for the entire frame. But that's a quite small search space. So, and some other simplifications that I have tried, which work well, is to select the damping used in the filter core based on the frame QP. And I have also tried to decide the number of bits to use per block based on the frame QP and based on the bit rate and frame type. And I think there are still many ways to improve the CDEF RDO. And the reason why I think it's important to have a good RDO for CDEF is that in a practical encoder, CDEF can probably replace some of the more complex tools, in particular in AV1.
Maybe not replace, but just help clean up.
Yeah, well, not replace from the standard, but if you want to do a real-time encoder, you probably won't, you can't use all the tools. It's simply too complex. Next slide, please. So these are the results that I got for adding CDEF in Thor. Here I'm comparing just doing deblocking and with deblocking plus CDEF. And in the low complexity case, the PSNR is 6.2%, and the Chroma PSNRs is even better. If you look at the IEDE number, it's actually 10.3%, which is, I think, is quite impressive. Even in the high delay configuration, it's 6.3, and in the high efficiency, it's still 5.2% and 3.1% in the low delay and high delay configurations. So that's not bad, I think. Next slide, please. And if we compare this with CLPF, so these are the gains that we get from replacing CLPF with CDEF. The CEIDE number is 2.2% in the low complexity, low delay configuration. And it drops to 1.1% in the high efficiency, high delay configuration. So it's not a huge difference, but the main reason to add CDEF is to improve the actual visual quality. And in AV1, we did some subjective tests comparing CLPF with CDEF. And even though the change was less than 1% in AV1, people could still tell the difference. So that probably points towards a real difference of at least 5%. Next slide, please.
Mo from Floor Mic again, virtual Floor Mic. Question on the the gains for Chroma look like about 3 to 4 times the gains overall. Any
Right.
clue why? That's a
I
pretty
don't
serious
have any clues, but
difference.
what I would like to investigate is whether there could be any bugs in the encoder. It could be probably not normative things that would have to be fixed, but it could be some kind of bug that CDEF is able to partially correct. But I don't really know. It's an interesting result. But we could always hope it is a bug and it will get further gains.
A good result. Sorry,
next
Mogan for floor mic again. So before you finish on CDEF, I wanted to raise one issue
Sure.
related to the requirements document that we expect some substantive changes in. I think one of them may be related to support of 422 Chroma format video. And I
Right.
believe CDEF is one of the barriers to that because the direction search does not support rectangular blocks. Is there
Right.
any plan to address that in any way?
So how it currently works is that in the case of 422, we'd still do the filtering as normal for the luma plane, but the filtering is disabled for Chroma. And
Disable all filtering or disable direction search only?
it's completely disabled, I think. So there are ways to address that, like skipping the directional part and basically doing CLPF. Tim has a comment.
Yeah, Tim Terryberry from the floor. The directional search is only ever done on Luma. So what normally happens is the Chroma uses the direction that Luma found to orient its filters. And since there isn't a direct correspondence between the directions we have in Luma and the directions we have in Chroma, when you squeeze the Chroma blocks into a rectangle, then we disable the filter.
I'm sorry, Tim, you're a little thin at the end. So what do you do for Chroma blocks then?
Just disable the filter completely.
Disable the direction search or totally disable the filter completely?
The whole filter completely. Because you can't disable the direction search. That's only ever done on Luma. What you could do is just assume a fixed direction, which is what Steiner was saying, and just always filter with that direction. And that would be essentially like CLPF.
Yeah, there are solutions, but currently I don't think those solutions, any of those solutions, are going into AV1, and it might be because people don't care. I'm not sure how important it is to have good performance for 422.
Well, I mean, like I said, I think there may be some changes to the requirements to make 422 more prominently supported.
Okay. Yeah, well, it is supported, but the compression will suffer slightly. Okay. Last time I had some graphs showing the compression and complexity trade-offs of AV1, and I have updated those. I also had some graphs showing comparison between the different codecs, and I haven't updated those since the difference in Thor and isn't that big. It's just 1%. So what I'm going to show are the compression speed relationships using RV compressed yet with the objective one-fast test set. And since IETF99, there's an improvement in AV1 of about 5%, and the encoder runs at roughly half the speed. And I've been using the low delay configuration, and the BDR anchor is AV1 as it was in July last year, which is roughly equivalent to VP9. So next slide, please. So starting in July last year at 0, the compression, the BDR number goes down, which is good. So at the last meeting, we had a BDR gain of about 20%, and that is now about 25%. And the graph has been steadily dropping with the additions of new tools in AV1. And there are still some tools left not yet enabled. So I expect this to drop slightly more. So we'll see. Next slide, please. And this is the complexity history. Note here that the y-axis is logarithmic, and the y-axis is the frames per minute, not day, not seconds, but minutes. It started at around 15 last year in July, and is now around 1 frame per minute. So there's a change of a factor of 15. And it seems to be flattening somewhat, but again, this is a logarithmic scale on the y-axis. So I think this shows that the compression gains that we have seen in AV1 don't come for free. It has a big cost. So if we compare VP9 with AV1, I think currently AV1 is basically a continuation of VP9 if you plot it with different complexity settings. So you have a bigger toolbox, and as you add more tools to the codec, you get compression gains, but you also get the speed penalty. And the question remains whether that toolbox is a better toolbox, not just a larger, so we could replace tools in VP9 with simply better tools and get better performance with the same complexity. I'm not sure, but if everyone gets adopted as and used as a standard, people will work on this for years, and it will probably beat VP9. But we can't prove that yet. Okay, this is what I had.
Can you just give a quick thumb in the air of what the complexity is absolutely right now? Not relative history, but absolutely to VP9, roughly?
Certainly more than 15 times. It's closer to 100 times, I guess. Yeah.
It was only 57 last time I checked, so I guess it's increased a lot. And wow.
So it will probably, it hasn't been a great focus to speed up AV1, so that will probably get more focus as the actual tools are finalized. But yeah, right now the reference encoder isn't that practical. We can't simply, I think the test specification says that we're supposed to run 4K sequences, 10-bit, but we can't practically do that now. So nobody has been presenting the test results according to the specs, actually, because it's simply too slow.
And so just to know that those numbers were for the encoder, and roughly what the decoder speed is?
The decoder speed is roughly 1/4 since July 2016.
Okay. So about 4x as complex as VP9. 4 times the complexity of VP9.
I think it's closer to 16 times, but I think the main reason for that is there's still some SIMD optimizations lacking in VP9. So I think 4 times is a more accurate number. Okay, thank you.
Thank you. All right, Tim.
All right, stand in the pink box. I'm Tim Terryberry. I'm going to be presenting work on the Dala transform design. This is joint work with Nathan Egge and Monty. So although I got this stuff started a few years ago, those two have really been doing the bulk of the work lately, so I think most of the credit of the recent developments goes to them. Next slide. So I'm going to talk a little bit about what our goals were in designing transforms for DALA. One should be pretty non-controversial, is we wanted an exact integer implementation. It's just the way that video codecs have worked ever since 264. There's lots of iterated prediction with unstable filters. So you want an exact specified implementation so that all decoders agree and there's no drift. We also wanted to be able to support many different variations of the transforms. So low bit depth, high bit depth, both square and rectangular, discrete cosine transforms, discrete sine transforms, etc. We also wanted high accuracy. So this is 2017, as you just heard. We can have lots of complexity. So in times past, people were afraid of having multiplies, and while we'd like as few multiplies as possible, we can have some multiplies in there if it gives us more accurate transforms. That said, we want to keep software complexity as low as possible, in particular paying attention to how things would be implemented in SIMD, and at the same time we want to have reasonable hardware complexity, which means we need low latency for small transform sizes, and for all of these variations we want to keep transform reuse and embedded designs in mind. So that stuff will come along as we go through some of the slides here. Next slide. So just to start us off, this is the 4-point discrete cosine transform for H.264. It is very low complexity, so you can implement this with 8 adds and 2 shifts. It has a few drawbacks. One of them is that it is a non-uniform scale transform. So the coefficients that you get out, even though the discrete cosine is this unitary transform where all the basis functions have the same magnitude of 1.0, this gives you out coefficients that have different scales that you then have to multiply by. And that usually gets absorbed into the quantization step. So you can say, oh, we're saving one multiply, but in reality, in the way encoders are designed today, we do rate distortion optimization with several different possible quantization levels for all of the different coefficients. So you actually need to do several multiplies in there in order to get a consistent estimate of distortion that backs out the scaling factor. And those extra multiplies get multiplied by the number of different options that you search in the encoder, which, as we just saw, can be quite a lot. One other thing is that when you start having larger and larger transforms, so this is only a 4-point transform, when you start going up to, say, 64-point transforms, you actually need a very large table of constants for all of these scale factors. So we added the new goal that we wanted to have uniform scaling for all of our transforms. And that will cost you 4 multiplies in this design. But as we go to larger and larger sizes, it turns out you can achieve this with much less than 1 multiply per coefficient. All right, next slide. So this is the VP9 4-point discrete cosine transform. And I may pick on VP9 a little bit today. It's not because I think the VP9 design is bad, but it's actually a fairly standard textbook design for transforms. But I think we can do a little bit better. And so I'm going to talk about some of the improvements we've made relative to VP9, just because VP9's transforms are the ones that I know the best. So this is the 4-point DCT. It actually has 6 multiplies. They are full 32-bit products. So if you look at the bottom there, we're actually taking 2 of these products and adding them together. So we need the full 32-bit result in order to do that. And then it additionally has 8 adds. 2 of those happen at 32 bits, and then 4 shifts. Right, next slide. So there are a few avenues for improvement. One is simplifying the multiplies. So if you looked at the 264 design, we could just scale the outputs of that transform, and it would only cost 4 multiplies instead of 6. but the 264 design is not a real DCT, it's only an approximation to a DCT, so it would be a little bit less accurate. But as we're going to see in a bit, we can actually do just as well with an accurate transform. So the other approach for improving things has to do with scaling. So the VP9 DCT adds this factor of a square root of 2 relative to a unitary transform. And in fact, it turns out as you make the transform larger and larger, each time you double the size of the transform, it adds an additional factor of the square root of 2. So this is sort of okay if you take the log of the width and the log of the height, and that comes out to be even. Then you can just correct the thing with a shift. But now we want to use rectangular transforms, like an 8x4 transform or something along that. And now this scale factor becomes odd. And so we can't correct it with a shift. We actually have to correct it by doing 1 multiply per coefficient in order to get something that matches the same scale as all of our quantizers. All right, next slide. So where does this scaling actually come from structurally? Next slide. This is sort of the textbook factorization of a type 2 discrete cosine transform. So it starts out with this stage here on the left, where we're basically computing sums and differences of pairs of pixels, sometimes called +1 -1 butterflies or something to that effect. And then after that, you can split the thing into a smaller discrete cosine transform and a smaller discrete sine transform. All right, next slide. So these butterflies here at the beginning are non-unitary. Like if you compute equivalent basis functions for that and say what's the magnitude of the basis function, it's 1 squared plus 1 squared is the square root of that is the square root of 2. Right? So that's where that factor comes from. Next slide. And because this is recursive, there's another one inside there. And as you expand the transform by a factor of 2 each time, you get an additional one of these factors of a square root of 2. And you also wind up having to do something in the discrete sine transform that is also expansionary like this if you want the scales to be uniform. All right, next slide. So we'd like to get rid of this extra scaling so that we don't have all these extra multiplies in our rectangular transforms. So one way we can do that is we can use multiplies. And in fact, if you go back and look at VP9's 4-point DCT, they actually already do this. So I don't know if you flip back to the slide 4. So this step up here is actually would be the same thing as a +1 -1 butterfly, but then it has scaled the outputs after that so that they match the discrete sine transform at the bottom there. So that's one way to correct this. Keep going. But that only got rid of it out of one stage, and we're getting a set of these at every stage. So that winds up being kind of expensive. So another approach is we can restrict ourselves to only using shifts and adds and use asymmetric scaling. And I'll describe what I mean by that in the next few slides. So there are basically 2 different options. The construct at the top there computes a sum and difference where the output of the second component is halved compared to what you would normally get. And then the next one computes a sum and difference where the output of the first output is halved compared to what you normally get. And as you see, you can do this with just by adding one shift in between the two additions or subtractions. So what happens is instead of doing an addition and subtraction and having both of the scales increase by a factor of square root of 2, what we're actually doing is increasing one by a square root of 2 and decreasing the other by a factor of square root of 2. So they become asymmetric. But overall, the scaling is unity. So like the determinant of this transform as a whole is still 1. And then we can cancel out this asymmetry in subsequent steps. So next slide. And to do that, we use constructs like this. So the first one there computes a sum and difference where it halves the second input, and then the second one does the same thing except it halves the first input. So these kinds of constructs can cancel out the asymmetry from the previous steps. So next slide. We'd also like, as I said, to simplify the multiplies. So all of these multiplies come from plane rotations between two variables. So we basically, in all of our transform factorizations, we've decomposed it into a series of these plane rotations where we are taking two values and we are rotating them by some amount. So we can actually, instead of doing that as a matrix multiply here, we have 4 multiplies and 2 additions. We can get rid of one multiply and instead add an addition by using a construct like that at the bottom here. Right, next slide. So we can actually also arbitrarily scale the inputs and outputs of these rotations. So just multiplying through, you can instead derive a series of steps which looks like this. And the important thing to note is that all of the complex stuff there is basically just reduces down to a constant. And so it's x0 minus a constant times x1, x1 minus a constant times p0, and then p0 minus a constant times y1. So this becomes very simple and can let us absorb scalings in the multiplies as well. All right, next slide. So the advantages of doing this, we get 25% fewer multiplies. In general, multiplies are much more expensive than additions in software as well as hardware. They all have this structure of x plus a constant times y. So when we do that in fixed point, it's going to be x plus a constant times y plus a rounding offset, and then we're going to shift shift it to the right and only take the high part of that multiplier output. So the advantage of doing this is that all of our 16-bit SIMD stays in 16 bits. So we don't actually need to compute full 32-bit products. We only need the top half. So if we actually had to go compute a full 32-bit product, we could only do that with half the throughput in a fixed size SIMD register. So SSSE3 and Neon actually both have instructions for doing exactly this kind of multiply. So it's a single instruction that will do the multiply, add the rounding offset, and shift the product over to the right. And so none of that has to expand out to a full 32 bits, so that whole thing fits in 16 bits. Next slide. So putting all those things together, we get a transform like this. So we start off, instead of having +1, -1 butterflies, we have these asymmetric scaling steps. We use both types so that we get scaled outputs in different directions that we then cancel in the next step. And then we have our rotation down there at the bottom gets replaced by one of these scaled rotations using only 3 multiplies. So we have 1 more addition and 3 more multiplies than the H.264 transform, but we have uniform scale. All right, next slide. The other thing, if you counted very carefully, there are 3 1/2s on the board, or on the slide, but I only say 2 shifts at the top, and that's because 2 of them are actually the same value. So as you get larger and larger transforms, you'll also be able to share more and more of these shifts between the stages like this, and that's just because of the way that we arrange them. All right, next slide. So expanding that out, we can do an 8-point DCT. Next slide. Or a 16-point DCT. And that keeps going up to 64 points. Yeah, it probably would have taken a few hours to make the drawings for that, so I didn't do that. But it took a few hours to make that one.
Imagine 4 of these.
But the other point to make is these things do have embedded structure. So both the endpoint DCT and the endpoint discrete sine transform are embedded inside a discrete cosine transform that is 4 times larger. So that embedding actually skips a level because of the asymmetries. So if you only go up one level, then we're actually taking asymmetric inputs, and so it's not exactly the transform we need.
So we basically need two sets of
Right. Yeah.
sets of
You
transforms and
need
embed everything from there.
Yeah, you need an even set and an odd set, essentially. All right. Next slide. So a few notes on accuracy. So all of these right shifts and multiplies introduce rounding errors. We want to keep those as small as possible. So we can, the way we go about this is that we shift up the input by some number of bits before we do any of the transform. And then we do the full forward transform, quantize, code, dequantize, inverse transform. And then on the other end, when we finally get down to pixels, we shift down the output again. So how much do you shift? Well, we found diminishing returns at about 4 bits. And that was enough to make all of the discrete cosine transforms match a double precision floating point implementation after rounding to the nearest pixel value. So with just a 4-bit upshift, we get the error down below 1/2 of a pixel step for 8-bit input. All right.
Is that, sorry, Mo from the floor, Micah, is that compared to the same approximation or compared to a full DCT implemented in double floating point?
That's a full, bog standard DCT,
Not any approximation.
straight from the formula, giant matrix multiply implementation.
That's good.
What about what? So the error winds up being the same for higher input bits, and I can go to the next slide. I'll talk about that in a couple of slides.
There we go.
Yeah.
Is that it?
That's it. Basically, the accuracy is less important for higher bit depths because what you actually care about is accuracy relative to your quantizer. And so higher bit depths use higher quantizers to get similar bit rates. So we shift up less for higher bit depths. Basically 10 bits is a 2-bit shift, and 12 bits we have no bit shifts. So it injects a little bit more noise, but it doesn't matter. But as a result, we can use the same transforms for all bit depths. All right, previous slide.
Mo from the floor again. So I think that also means you can use the same SIMD one right for
Yes.
all the input bit depths.
That's
right?
that's correct. You can use the exact same implementation.
That's nice.
All right.
Go back. Where to?
Yeah, next slide. So how does this compare with VP9? So VP9 also shifts up the inputs, but by not as many as 4 bits. And then it shifts down the outputs by more than 4 bits. And actually has to do it sometimes in between row and column transforms too. And that's because they have this extra factor of a square root of 2 that they grow by every transform size. So what's actually happening is the scale of these VP9 coefficients grows as the transform progresses. So any rounding errors that you introduce early in the process get magnified as that scaling increases. Whereas in Dala, all the stages have the same scale, so all of the rounding errors are injected at the same level, and they do accumulate, but we don't magnify them. All right, next slide. That's the one we just did. So another important point to talk about is the difference between scaling and dynamic range. So everything here has orthonormal or unitary scaling, right? So the magnitude of the basis functions is 1.0, but the dynamic range of the output still increases. So the dynamic range here, I mean the minimum or maximum output values you can actually have. So all of your unitary transforms are essentially n-dimensional rotations, and you can think of the input as a big n-dimensional box, and the length of the diagonal of that box is going to be longer than the length of any of the edges. So as you rotate it, you can get larger values than you started with. In fact, it's by a factor of square root of 2 every time n doubles, which is in addition to the scaling that VP9 does, they're not the same scaling. So we still have this factor of square root of 2 and the size of our coefficients, but that's okay because the L2 norm is still preserved by the transform. So the question you might ask is, how big can the outputs actually be? Next slide. So with a 4-bit upshift, all of the transforms with 64 pixels or less fit in 16 bits. So that's a 9-bit residual, a 4-bit upshift, and then 3 bits of dynamic range expansion, which is half a bit for each of the powers of 2 and 64. So that includes your 4x4, 4x8, 8x4, 8x8, 4x16, and 16x4. All of the column transforms all the way up to 64 point also fit in 16 bits. So that means that 16 bits is the maximum size that you need for a hardware transpose buffer. So in between row and column stages, the hardware has to buffer the coefficients so it can transpose them, which is a fairly significant gate cost. So being able to keep that small is nice. It also means that when you're writing SIMD, you can write a SIMD for the row transforms and a SIMD for the column transforms, and it all fits in 16 bits, and for all sizes. And then you can have a separate version once things start going larger than 16 bits. So comparing to VP9, they have larger intermediaries in the transforms, but they always shift their final coefficients down to fit in 16 bits. So we think this is a misoptimization. It's actually just as easy to do the shift down and pack while you're doing quantization. So we have not tried to do this extra shift at the end. It also helps avoid double rounding and simplifies rate distortion optimizations, so you don't have to have any special cases for different scale factors depending on your block size. All right, next slide.
Quick question, Mo from Floor Mic again. So you don't have a fixed shift between the row and column stages. You accumulate a certain number of pixels, total pixels first, before you do your shift?
So we don't have a shift between the row and column stages at all.
What if you have bigger than a 64 pixel?
So if you have bigger than 64 pixel, then we start going to wider SIMD once the values start exceeding 16 bits.
So you just go bigger than 16-bit intermediates.
Yeah.
That would never shift down.
We never shift down.
Okay.
I mean, you can shift down after you quantize, right? Because when you quantize, you're going to have the same values you would have had regardless of what your shift was. But yeah, I mean, the point is you're going to have to go up to 32 bits in the transforms at some stage. Because we've eliminated this extra scaling, we do that at a later stage than VP9 does. And also because we don't do extra upshifting for high bit depth, we do it at a later stage than VP9 does. So we can keep you in 16 bits longer. But yeah, I mean, at some point you do have to go up to 32 bits, and that's true both in VP9 and in us, okay, for the larger transforms. All right, so a few notes on reversibility. So when you have steps of this general form where you take a variable and you add to that variable some function in all the variables except the one you're adding to, that's called a lifting step. There can be an arbitrary, like that function can be arbitrary. It doesn't have to be linear, like it has no special properties at all. But because the function is not a function of the variable you're modifying, it's exactly reversible, right? So on the decoder side, you can just subtract off that function and get exactly the value that you started with. What that means is we can make inverse transform by just reversing all the steps of our forward transform. And so it turns out that all of the steps that I have described so far that we use to build our transforms happen to be lifting steps. All right, so why is this good? Why would you want to do this? So we really wanted reversibility in Dala because we used lapping instead of a deblocking filter. So deblocking filters have this nice property that they're low pass, so they tend to blur out details over consecutive frames. Whereas on the other hand, forward and inverse lapping are matched. So any details that you have do not get blurred out by applying the lapping filter. They instead just get shifted around, and when you apply the opposite of the lapping filter, then they get restored. So if those two are not exactly matched, then you'll build up these rounding errors over multiple frames, and this is the same problem of, we essentially have an unstable filter. So because we have an exact integer specification of our transforms, you would never get encoder-decoder mismatch, but it would cost bits to correct these rounding errors in the encoder. So that was bad. All right, next slide. Do we actually need perfect reversibility? So it seems to help. Compared to transforms that don't have it, we've seen some small coding gain improvements, but it's probably not required, but we get it basically for free from the structure of our design. We don't actually have it in DAL anymore. So when you do this 4-bit upshift and then do the transform into the 4-bit downshift, that downshift is not reversible, so that breaks it. You can restore it by using 12-bit references, even if you have 8-bit input data, basically just avoiding the downshift down by 4 bits at the end. And there's a nice blog post there by Monty that goes through and shows you what this error buildup looks like and what happens when you switch to 12-bit references, and it essentially goes away. But it turned out also that just using CLPF from Thor or the Dollar deringing filter solves the problem by adding essentially one of these low-pass filters back that we didn't have in our deblocking filter. So that prevents these errors from building up. Right, next slide.
Mosinati from the floor mic again. So this is the implementation in DALA that is not reversible because of downshift. What about AV1?
So AV1 also has this 4-bit upshift and 4-bit downshift, so it's also not exactly reversible. Right?
So only if you use 12-bit internal bit depth will you get the invertibility.
Right. So and also to be clear, I'm talking about invertibility between going from coefficients to pixels back to coefficients, right? Which is the step we needed for the lapping filter.
Right.
So you still have invertibility in the sense of going from pixels to coefficients back to pixels.
Right. Yeah. So where I was going with it is, if you had a skipping the quantizers, then you could do lossless coding with a real transform instead of the current 4-point
right
Walsh-Hadamard transform.
So
if there's gains.
That's actually something we tried back in VP9 with an early version of these transforms. And I think just replacing the 4-point Walsh-Hadamard transform that they use with a 4-point DCT was about 25% worse in terms of the lossless bit rate.
Right.
So I don't know if you allowed using larger transform sizes, if you instead of just fixing everything down at 4
an adaptive RDO over
right
adaptive transform size.
You may be able to do slightly better than that, but just doing a straight swap of 4-point DCT for
we saw the same thing with H.264 high profile. Somebody blindly implemented high profile and switched everything to 8x8. You see loss, but if they intelligently switch between 4x4 and 8x8, there's usually considerable gain. So maybe adding some heuristics to optimize that may end up with a pretty good lossless codec.
Yeah. All right, next slide. So the other nice feature of reversibility is the effect it has on dynamic range, right? So as we said, the transform coefficient values are larger than your Pixar values because your forward transform expands the dynamic range. Your inverse transform is also an n-dimensional rotation. So how do we know that it doesn't expand dynamic range? Right, like if I have two coefficients x0 and x1 and they both just barely fit in 16 bits, how do I know that x0 plus x1 won't overflow? And the answer is because the transform is reversible. So all of the values that I compute in my inverse are going to be the same as in my forward transform, plus or minus any quantization error I've introduced. So this means that I'm only guaranteed to avoid overflows if the coefficients come as the result of transforming pixels. So if I decode random garbage, I might get random overflows, but we can just define that those cases are undefined behavior, right? So I don't think anybody actually cares about the quality of decoding random garbage. That's the same approach 264 took. One note about discrete sign transforms: there are two types that we care about. Type 4 and type 7. So for interprediction residuals, the prediction error you get is asymmetric. So the error close to the edges you're predicting from is much smaller than the error far away from those edges, which means you want an asymmetric transform to code them. And if you say, okay, what's the optimal transform to use? it winds up being this type 7 DST, and you get that by taking a linearly increasing correlation matrix and taking the limit as the correlation approaches 1 and solving the eigensystem and say, what do you get? The type 7 DST pops out. So type 7 DST factorizations are much nastier than the type 4s, which are the ones that we have embedded inside of our DCT. So the type 4 is there at the top, and the type 7 is this thing down here. And the real problem is this n plus a half thing inside your trig functions, which means what this actually is a trig transform embedded inside of a 2n plus 1 size fast Fourier transform. And so pulling that out of there and still retaining a fast algorithm is a bit messier, since it's not a power of 2. So next slide. Type 4 transforms turned out to be almost as good, and they're already embedded inside of all of our DCTs. But our current approach is that we use type 7s for the very small ones, currently only 4.8 byte, and then use the embedded type 4s for all of the larger DSTs. So the small ones, the factorizations don't get that bad, and it turns out to be where you can get at least some gains by using the correct DST. Next slide. So comparing overall complexity, the first 3 columns there are dollar TX. The next 3 columns are TXMG, which is sort of the AV1 extension of the VP9 transforms to handle all these things like rectangular transforms and unify high bit depth and low bit depth, etc. So we generally have a few more adds, but not that many more adds. You can see like for the 32-point DCT, it's 6.2 versus 6.0. But we have far fewer multiplies per coefficient, right? Like again, for that DCT, 2.7 versus 4.1. So we actually can wind up with 39% fewer multiplies, I think, for the 32-point DST. We actually implemented the SIMD for the 8-point DCT and directly compared that to the existing SIMD for the AV1 transforms, and it was benchmarked at 26.2% faster, and that's mostly a result of using fewer multiplies and using cheaper multiplies, right? So none of our multiplies have to go up to a full 32-bit product, and we don't have to do any 32-bit additions, so we're able to get higher SIMD throughput. I was going to say, just a small note for the discrete sine transform. We're using the type 7, while TXMG is only using a type 4 for the 8-point discrete sine transform, which is why ours is a bit more complex, particularly on the additions. And that's just a result of the type 7 factorization is not as good. All right, so a few hardware considerations. Interprediction requires reconstructed pixels from your neighboring blocks. So if you think about it, this serializes the reconstruction of those blocks, including the inverse transform part of that reconstruction, which is a particular problem for encoders. And the decoders, you can sort of start the transforms early, and it only serializes adding the residuals. But on the encoder side, you need to know what pixels to transform. So that part becomes completely serial. Unfortunately, when we do our 3 multiply rotations, those multiplies are all chained consecutively. Like each one depends on the output of the previous one, which winds up being a bottleneck for small transform sizes for hardware. All right, next slide. So just for the 4-point DCT and DST, we've replaced them with transforms that are not perfectly reversible and not lifting based. But we basically replaced the 3 multiply block with a 4 multiply version that's just like the matrix multiply. So all the multiplies proceed in parallel, but we still only use the top half of that multiply output, so we still get full SIMD throughput. And then for the DST, we use a custom factorization that reduces to 5 parallel multiplies. So I said these are not exactly reversible, but they do solve the hardware latency problem. Next slide. So additional consideration, most hardware is already multi-standard and includes VP9 in all of the VP9 transforms. And so they dedicate a lot of gates to having lots of parallel multiplies. So we can replace a bunch of the serial multiplies in our rotations with these parallel multiplies without introducing any additional multiplies. And so anything that's of the form, x0 plus a times x1, u0 plus b times u0, and then y1 plus a times x1, where we have this ABA structure for the constants, we can replace with this little more gnarly looking thing on the right. But if you reduce it down, it's one addition, 3 multiplies that all happen in parallel, and then 2 more additions. So it's the same number of operations, but the multiplies can happen in parallel. So this is, again, no longer exactly reversible. So we're still experimenting to see what impact that has on accuracy and making sure it doesn't introduce any new potential overflows that would prevent us from keeping our SIMD in 16 bits. So that's everything on the design of our transforms. I guess anybody have any questions? I think we went through most of Mo's during the presentation. So,
Mo's Nash from the floor again. I had one more final question.
Sure.
Kind of a broad one. So these look like they compare. These transforms look like they compare very favorably to VP9 and AV1. Have you looked at Thor, which is basically HEVC? Have you looked at comparisons to the Thor transforms or the HEVC transforms?
So we haven't done direct comparisons, at least in terms of, for example, coding performance. In terms of complexity, like I think if I understand correctly, the Thor transforms are basically giant matrix multiplies. And so, that you can get away with that for very small transforms, but as they get much larger, I think that this will wind up being significantly faster.
All right. Okay. About 15 minutes behind. Luke, you can use the rest of the time if you want, because I think we technically have the room until 11:30. But if you want to speed up, 11? That was 11:30. The next session starts. Okay. All right. So Luke, you got about 5 minutes if you can.
I suspect you can actually go to about 11:15 because the new chairs won't need a whole half hour to set up. So.
Okay. Thank you. So Luke, just try to go quick on whatever you can.
Can you hear me?
We can.
All right. So, you have the slides up for my presentation?
Can you see them?
No, I can't see them.
I'm on slide 1.
Okay, I can see them now. So, yeah, I'm going to present an update to the SCFL draft for NetVC. So if we go to the first slide, Chroma from Luma is essentially an intra-prediction tool, so it has no dependencies on other frames. It is only available to Chroma planes, and it basically works by predicting Chroma pixels using coincident reconstructed Luma pixels. So let's go to the next slide to see the difference from what we proposed before. So prior proposal was on a DAL implementation, so now we've changed that to reflect what was proposed for AV1. Most significant change is that we no longer rely on PVQ. So prediction is now done in the spatial domain. We consider only the AC contribution of reconstructed pixels. I'll talk about that a bit later, but that is similar to what was happening before in the PVQ version of CFL. We use the existing DC pred, so DC prediction, for the Chroma DC contribution. This is already available in AV1. There's already fast implementations. It requires no signaling, and it is more precise than what was used before. So that's also very interesting. So going on to the next slide. So the differences, we can talk about maybe Dala and Thor, which are codecs that people know here. As I already said before, we went away from this frequency, and we're now going for the spatial domain for prediction. The Thor implementation is implied in the signaling. The DAL implementation used the PVQ gain and the sign bit to send the information. We send the information explicitly using joint signs and an index value. The activation mechanism was a threshold for Thor. It was also signaled in Dala. We have a special UV only mode in AV1. So AV1 has separate prediction modes for intra luma and intra chroma. So we take advantage of that to have this UV only mode called CFL pred. We do encoder, instead of doing encoder model fitting, we will do a rate constrained search, and we do no decoder model fitting since the information is signaled in the bit stream. Moving on to the flow of the operations, we see that if subsampling is used, so if chroma subsampling is used, the luma surface will not be the same as the chroma surface, so we must do a luma subsampling that is equivalent to the chroma subsampling that's being done. We subtract away the average. This gives us the AC contribution in the spatial domain, and this is usually on a chroma transform size block. Then we'll decode the signals scaling factors from the bit stream, and we'll multiply that. These are in Q3 precision, but then once we multiply, that goes down to Q0, and we add in the DC pred, the chroma DC pred to that value, and that gives us our final prediction. So if we look at the codebook that we end up with on the next slide, oh, okay, never mind. Oh, that's good. Okay, so, all right. So basically, why do we go with the chroma DC pred is that when we use the AC contribution, this AC contribution is zero mean, which means that it sums to zero, and doing so simplifies the linear regression equation for beta, which makes it the average of the chroma reference pixels, and the DC pred is a very good predictor of that, as it tries to predict it using the neighboring pixels that are adjacent to the above and left borders of the block, and it requires no signaling, so we don't have to signal the beta value. So alpha will be signaled, but beta won't. Moving on to the next slide, we have the scaling codebook. So basically this shows you when we do the search, what happens. So we start in the middle of this grid, and we can change the scaling factor for chroma correction with chroma CR and chroma CB, and we move from negative to positive, and you can see all the different tones that you can get. This, of course, is only a subset of the codebook we have. It goes from -2 to 2 in Q3, so that it goes up in steps of 1/8. 0 is not allowed as it is DC pred. We pick our value using a rate constrained search, as I said before. Since we are signaling the alpha value, we can't use a linear regression because that value won't be RD optimal. So what we do instead is we do the same thing as any other parameter in the encoder that requires rate, is that we take the weighted rate and add that to the distortion value and pick the parameter that minimizes that, and that gets signaled to the decoder. The next slide will explain how we go about signaling this. So we will join both signs. So there's going to be two scaling parameters, one for CR and one for CB. So we join them together. A sign can either be 0, negative, or positive. And since 0 isn't allowed because that's DC pred, we have 8 values, which we send to our multi-symbol encoder as an 8-value symbol. Now, for each non-zero scaling factor, we will send a value excluding 0, but all the way to 2 inclusively. And this, again, with a step of 1/8, this gives us 16 values for our multi-symbol. And this actually maxes out what our multi-symbol entropy coder can give us, which is a 16-value CDF. Going on to the next slide, we can see results from our analyzer. There's a link you can click there. Sadly, it got moved behind the image. You can see the distribution of how many times modes get used. So these are UV modes that in AV1. We can see that there's about 44% of the time DC pred will get picked, but as CFL comes in at about 17%, we observe it between 15 and 20% in different sequences for AV1. As you can see, the other contender modes or best mode are still slightly below. So we see that it actually outperforms other chroma modes that are available in the encoder. And you can actually see this live in the analyzer in real time. Moving on to the results for subset 1, we can see that there is a minus 4.65 CIEDE2000 value. This is a percentage. It is the BD rate, so it gives us a rate decrease with the same level of quality. We use the CIED value because it is the only one that considers both luma and chroma and does so in a perceptually uniform way. If you click on the links below, you can see the full breakdown with all the values. So subset 1 are still images, and objective 1 fast are video sequences. As you can see in that point, we are giving about an on average 2.41% reduction. This is for a single tool, CFL, over all of AV1. So that's pretty interesting. There's also PSNR gains. These are luma PSNR gains. The reason for that is since we have better predictions, we actually reduce the amount of bits. So and that gives this metric actually gives better gains because it has the same level of quality, but it'll have fewer bits to do so. And since this is the area between a rate difference and quality, that'll give you a negative value. So that's very good. If we move on to the next slide, we see that it is actually very good for screen content coding. So here we have on average about 5% reduction for the gaming Twitch dataset, which is on slide 11. Yes, so notable mentions here are the Minecraft sequence. So CFL alone gives a minus 20% reduction on both Minecraft sequences that are in that test sets. And we see also good results for GTA and StarCraft at about 5% each for CIED 2000, and still some significant gains for PSNR Luma only. So yeah, we're really impressed with the results from this tool, and that's why we're proposing it as an update for the CFL proposal for NetVC. Did I do that in good timing?
Perfect. Thank you very much, Luke. Thanks for compensating for Tim, the time usurper. Any other questions for Luke on the Chroma from Luma tool? Any other final items off the agenda? All right. So make sure that get the blue sheets signed if you came in late. Anyone still here from NetVC? Please make sure to get the blue. And where is the blue sheet, by the way? Right there. Anybody needs it? All right, please raise your hand and we'll get it to you. Otherwise, thank you very much. I'll see you in 101. Thanks, Matt, for standing in for our co-chair. Sitting in. You take my bag, I'll take yours. Summarizes the slides. That was way more than yeah, he goes above the and dongle. I have no idea. Were you here at the very beginning of the session? Beginning, we talked about how holes are